In this video, we discuss the mean value theorem. It's actually a generalization of Rolle's theorem, or you can think of Rolle's theorem as a special case of the mean value theorem. This is a very important theorem. A lot of other theorems and other results are based on the mean value theorem. So I know in Calculus 1 it might feel like this isn't that important, but it's actually very important in the grander scheme of mathematics. And I think you'll see why it's important, at least in applications, in just a minute when I tell you what it says. So this says, the mean value theorem says, let f be continuous on the interval from a to b and differentiable on the interval from a to b, the open interval from a to b. So we have the same three conditions that we started Rolle's theorem with. The function has to be continuous. We have to be talking about this function on a closed interval from a to b. And third, the function has to be differentiable on an open interval from a to b. If all of those things are true, then there is at least one x value, which we're going to label C, in the interval from a to b, the open interval, so not including the endpoints, such that the following is true. ST is an abbreviation for such that f prime of C is equal to f of b minus f of a over b minus a. Now notice that if f of b and f of a are the same, this would be 0, and so then I'd have f prime of c equals 0. That's Rolle's theorem. So Rolle's theorem is just a special case of this. But let's think about what this means when f of b and f of a aren't the same. Well, on the right-hand side, you might recognize this as the average rate of change of the function. I'm going to abbreviate rate of change ROC. It's the average rate of change of f on the interval from a to b. We also call this, geometrically, the slope of the secant line. Through 2 points, A f of A and B f of B. Okay, so the mean value theorem says if our function is continuous on the interval from a to b, so it can all be drawn in one piece, and it's differentiable, so there are no sharp corners. This is well defined everywhere. Or the derivative is well defined everywhere, excuse me. This says there is at least one x value in the interval from a to b such that the average rate of change, or the slope of the secant line through x equals a and x equals b through those 2 points on the graph, is equal to this. Remember what this is. The derivative is the instantaneous rate of change. Of the function f at x equals c. Or, in other words, geometrically, that's the slope of the tangent line. So, with these interpretations in mind, let's read this again. This says, the mean value theorem says if the function f is continuous, so I can draw it all in one piece on the interval from a to b, including a and including b, so we get all the points in between and we have endpoints. And it's differentiable, so that means it's nice and smooth, no sharp corners on the interval from a to b. Then there's at least one x value where the slope of the tangent line, that's the derivative value at x equals c, is equal to the average rate of change, or the slope of the secant line, through these 2 points. So maybe my graph looks like this. It's like we took Rolle's theorem and we turned the whole graph on its side. That's how I always like to think of it. Maybe this is our graph. The average rate of change of f on the interval from a to b is the slope of the line that passes through these 2 points. So here's my secant line. And a secant line is just a line that passes through 2 points on the graph of the function. And the slope of that line is f of b minus f of a divided by b minus a. Now this is saying that there is some x value in between a and b where the tangent line is parallel to that secant line. So the tangent line is going to have the same slope as the secant line. And if the two lines have the same slope, they're parallel to each other, right? Hope you said yes. Parallel lines have the same slope. It's okay if you don't remember. Now you know. Now I'm just going to try to guesstimate where does the tangent line seem to have this slope. I think right there. I'm trying to make it parallel. Do the best I can. Right there. So that's the value of c. Now, this only holds, we're only guaranteed to have this behavior where we have one tangent line that's parallel to the secant line if the function's continuous, so it can all be drawn in one piece, and differentiable, so there are no sharp corners. And this is a very important result. And I always think of this in terms of speeding. Your average rate of change, your average speed versus your instantaneous speed. I think police departments are actually using the mean value theorem sometimes to determine whether someone was speeding on some interval. So this is how it would work if they were trying to determine if someone was speeding. Let's say you're on the highway and you go 150 miles in 2 hours. Well, let's say you're going 160 miles. Okay. If you went 160 miles in 2 hours, what was your average speed? I hope you said, well, you take your 160 miles and you divide by your 2 hours. And you were going about 80 miles per hour. Now that does not mean you were going 80 miles per hour the whole time. You may have stopped at a rest stop. There may have been points when you were going 90 miles an hour. There may have been points where you went through a certain part of Oklahoma where you have to slow down because they've got a speed trap and they've got signs everywhere and you have to slow down. So you slowed way down because you're going through that small town, but then as soon as you get out of that small town, you started speeding again. But if you went 160 miles in 2 hours, your average speed was 80 miles per hour. Doesn't mean your instantaneous speed was 80 miles per hour the whole time. You weren't going exactly 80 miles per hour for 2 hours, for every moment in that 2 hour window. But this is what the mean value theorem says. If your distance function is continuous, and it is. It's got to be a continuous function. You don't get to skip any distances as you go through as you're driving. So if it's continuous and it's differentiable, so you don't have any sharp changes in speed, there's at least one x value on the interval from A to B where your instantaneous rate of change, so that is your instantaneous speed, is equal to your average rate of change. So this would actually be a really smart way for police officers to catch speeders, and I think they do this using, I don't know, some kind of technology when you're driving along the highway. They're able to say, okay, at this point, this person with this driver's or this license plate number was here, and 2 hours later they were 160 miles away, or 2 hours later they showed up at this other point, which is 160 miles away, and then they're able to calculate your average speed. This average speed doesn't tell me that I was going 80 miles per hour the whole time, but the mean value theorem says this: there was some point within that 2 hours where my instantaneous speed was 80 miles per hour. I may have slowed down a little bit sometimes and speeded up a little bit at other times, but the mean value theorem says there's some point when my instantaneous speed is equal to my average speed. And using that, we'd probably catch a lot more speeders, because we'd find out when people's average speed was this, even if we couldn't, if the police officers weren't able to get them with one of those little guns and calculate their speed at the moment that they're speeding. Calculus would enable us to figure out, well, they had to have been speeding at some point during that 2 hour interval. And they had to have been going this fast. Instead, you're driving down the highway and then you see the police officer and you slow way down, and they aren't able to figure out whether you're speeding or not. So that's just one real world application of the mean value theorem. But this is, again, a very important result that comes up in other proofs in mathematics a lot. So remember what it says: if the function's continuous and differentiable, there is an x value on the interval from A to B if the function's continuous on the closed interval from A to B and differentiable on the open interval from A to B. There is some x value on that interval where the instantaneous rate of change, so that's the slope of the tangent line, is equal to the slope of the secant line. Okay. Or geometrically, the tangent line is parallel to the secant line. The questions for the mean value theorem are very similar to the questions for Rolle's theorem, so we're going to do the same thing that we did with Rolle's theorem for mean value theorem questions. We want to determine whether the mean value theorem can be applied to a function on an interval. So we need to check three conditions. We need to make sure we're on a closed interval, and we always will be, because that will be given to us, like the -1 to 3 or the 1 to e and so on. We need to check to see if the function is differentiable and continuous. And for continuity, really we're just making sure the function is well defined. So we want to make sure we're not dividing by 0, we're not taking even roots of negative numbers, and we're not taking the logarithm of a negative number or 0. If all of that is true, the function is continuous, provided that it's defined by one of these formulas that we studied in previous classes. And if the function is continuous and differentiable, when we say it's differentiable, we mean when we compute f prime is well defined. There's no division by 0, no even roots of negative numbers, and no logs of negative numbers or 0. If both of those things are true, then there is at least one x value where the slope of the tangent line is equal to the slope of the secant line. Or you can think of it this way: there's at least one x value when your instantaneous rate of change, so that's your rate of change at an instant, is equal to the average rate of change over the entire interval. Okay, so we need to check differentiability and continuity for these guys. Now actually, with this absolute value function, I know what absolute value looks like. Y equals the absolute value of x looks like this V shape. So this is just a transformation of that. We could define this as a piecewise function, but that would be much more complicated than just graphing this function on this interval and seeing if the sharp corner is there. If the sharp corner is on that interval, then the function's not differentiable at the sharp corner, and therefore the mean value theorem does not apply. So let's take our function y equals f of x here and rewrite it so that it looks like a transformation of this guy. Well, one way that we can do that is we can factor out 2 from the x and the plus 1. And you might be saying, why would I do that? I would do that so that I can see the vertical stretch that's implied by this 2, and so that I can see the horizontal shift implied by the number over here. So I ask myself, 2 times what gives me 2x? X. Then 2 times what would give me a 1? I know it doesn't seem to factor nicely, but it's okay. We can use a fraction here. 2 times 1/2 would give me a 1. So I can factor that 2 out. Absolute value of 2 is just 2. And we can see that we've got a vertical stretch of our function. So I'm taking the absolute value of x plus 1/2 graph and I'm making it twice as tall. And this plus 1/2 leads to a horizontal shift. We take the y equals absolute value of x graph and we shift we shift 1/2 of a unit to the left. So this graph looks like this. Here's -1. When x equals -1/2, y is 0. And let's see, what do we get when x equals 2 here? When x equals 2, y equals 2 times 2 is 4, 4 plus 1 is 5. When x equals 3, we get 2 times 3 is 6, 6 plus 1 is 7. So this is not to scale. So when x equals 2, y equals 5. When x equals 1, y equals 3. When x equals 0, y equals 1. And then when x equals -1/2, y was equal to -1/2. When x equals -1, 2 times -1 is -2. -2 plus 1 is -1. The absolute value of -1 is 1. So we just get this part of that V shape, and it's not a perfect graph, but you get the idea, because I want the part of y equals 2 times the absolute value of x plus 1/2 on the interval from -1 to 3, because that's what they told us. Now remember, we're trying to determine whether the mean value theorem can be applied to this function on this interval. We need to check for 2 things: continuity and differentiability. F is continuous. On the interval from -1 to 3, because all absolute value functions are continuous. This is just a transformation of a basic function from pre-calculus. Now the other thing we have to check for is differentiability. It's not differentiable. We have a sharp corner at x equals -1/2. And x equals -1/2 is in that interval. So I'll say f is not differentiable on the interval from -1 to 3 because, let's say, f prime of -1/2 is undefined. So the mean value theorem does not apply. So you're checking for two things, continuity and differentiability. Absolute value, as soon as I see absolute value, I'm thinking sharp corner, it's probably not going to work out very well. Okay. Now, with logarithms, well, there are domain issues here. In order to determine whether the mean value theorem applies, we still need to check for continuity and differentiability. This function is well defined whenever the expression inside the logarithm is positive, because we can't take the log of a negative number or 0, not in the real number system. So this function is continuous as long as x is positive, and we're on this interval, so x is positive. So f is continuous on the interval from 1 to e, because x and natural log of x are well defined. We're not dividing by 0, we're not taking even roots of negative numbers, and we're not taking the log of a negative number or 0 because we're on the interval from 1 to e. So f is continuous. Now we just need to check differentiability. And I believe f is differentiable. And we'll say because f prime is well defined. And how do I know it's well defined? Because when I take the derivative, I get a function that's well defined. So let's prove that. When I take the derivative of this, I will use the product rule. We have the derivative of the first function times the second undifferentiated, so I'm just leaving the natural log of x alone, plus derivative of the second function times the first function. And the derivative of x is 1, and the derivative of natural log of x is 1 over x. So we've got natural log of x plus 1 over x times x, and the x's reduce, so we just get natural log of x plus 1. That's our derivative. That's well defined on the interval from 1 to e. Because this is continuous and adding 1 to it, it's still continuous. Okay, so the mean value theorem applies. So we'll say since f is continuous on 1 to e and differentiable, well, maybe I'll write out the whole word, differentiable on the open interval from 1 to e, the mean value theorem applies. And in order to use the mean value theorem, we've got to do two things. It says, if the mean value theorem can be applied, find the values of c in the interval from a to b such that the derivative at c is equal to the average rate of change of the function on the interval. So the first thing I like to do is find the average rate of change. And then I'll take the derivative and I'll set it equal to the average rate of change and then solve for x. Okay, so we know that the mean value theorem applies. The next step is to find the average rate of change on the interval from a to b. And in this case, a and b are 1 and e. So I need f of b, which is e, minus f of a, which is 1, all over e minus 1. That's f of b minus f of a. Now f was x times natural log of x. So I'm just replacing x with e and 1. Well, natural log of 1 is 0 because e to the 0 power is 1. So that's gone. That's 0. And natural log of e is 1 because e to the first power is e. You can also think of the log and the exponent as undoing each other, and when they undo each other, you're just left with that exponent e. Exponential. The logarithm base e and the exponential base e undo each other, and we're just left with the exponent there. So we just get 1. So our numerator is just an e, and the denominator, this is e minus 1 times 0, so e minus 0, which is e, all over this. So this is our average rate of change. Now, I don't have a very good sense for what e divided by e minus 1 is. E is about 2.7, so this is about 2.7 divided by 2.7 minus 1. But let's get a numerical approximation. Get e divided by, open parentheses, e minus 1, close parentheses, enter, and we get about 1.58. So that is our average rate of change, or the slope of the secant line. And we're going to draw some pictures for this too. So what have we done so far? Our function is x natural log of x, and we just found that f of 1 is 1 times natural log of 1, which is 0, and f of e is e times natural log of e. Natural log of e is 1, so that's e. So our graph looks roughly like this right now. Here's x equals 1, here's x equals 2, here's x equals 3, and e is about 2.7, so it's somewhere in here. So let's just call that e. When x equals 1, y equals 0, and when x equals e, y happens to be e. So there's 2, there's 3, and we'll say that e is about right there. Doesn't have to be perfect, but we try. We try to make a decent looking graph. Okay, so our graph looks roughly like that. Here's one endpoint and there's the other endpoint. Then we said, hey, let's draw a secant line through that. And the slope of the secant, that's your average rate of change, was e divided by e minus 1, which is about 1.58. Now, we're guaranteed by the mean value theorem that there's some x value on the interval from a to b, which is 1 to e in our case, where the slope of the graph at that x value is equal to this value. So once you have found the average rate of change, the next thing you do is you set the derivative equal to the average rate of change and solve for x. If you want, you could call that f prime of c and solve for c. It's the same thing. So we've got f prime of x. We calculated that earlier. It was natural log of x plus 1. We're setting that equal to e over e minus 1. And we're trying to get x by itself. So the first thing I would do is I would subtract 1 from both sides, and we get natural log of x is e over e minus 1, and we're subtracting 1. Now, I'm going to write that 1 as a 1 over 1, and then I want to get a common denominator. This denominator is e minus 1, so I'll multiply by e minus 1 over e minus 1 over here. Now since we have the same denominator, we can just subtract the numerators, distribute that negative to both terms, so we'll have e minus e plus 1. So the e's reduce. Now we've got natural log of x equals 1 over e minus 1. And to get rid of the natural log, we're going to use the base e. I know it looks bad, but that's just the number. X is equal to e raised to the 1 over e minus 1 power. I don't know what that is, but I can find an approximation. Hopefully it's between 1 and e. It's supposed to be. So I'll do e raised to the 1 divided by, open parentheses, e minus 1, close parentheses, and we get 1.789 or 1.8 approximately, or 1.79. So they're telling us when x equals 1.79, the graph is, or the tangent line to the graph is parallel to this tangent line. Just to draw the graph a little bit better, to see where that point lies, let's evaluate the original function at this value. So I'm trying to find the y value that goes with this x value. So I'll just substitute this for x into the original function. So y was x times natural log of x. And I'm replacing x with e raised to the 1 over e minus 1. And these guys undo each other, because the log base e and the exponential undo each other. And so we just get e raised to the 1 over e minus 1 times 1 over e minus 1. This looks really horrible, but it's just a number. Don't be intimidated by it. That's our y value. So it looks like we've got x in the numerator, and then we're dividing by e minus 1 in the denominator. We're dividing by e minus 1. So the y value there is approximately 1.04. So when x is about 1.79, y is about 1.04. So maybe that point's on the graph. So maybe my graph looks like this. And at that x value, it's kind of hard to see. The tangent line is parallel to that secant line. Okay, so the mean value theorem did not apply here because we had a sharp corner. The mean value theorem did apply here because the function was continuous and differentiable. So when we're determining the values of c that are guaranteed to exist by the mean value theorem, we got to do two things. First, we find the average rate of change of the function on the interval. That gives us the slope of the secant line. Or geometrically, I can draw it. The graph goes through x equals 1, y equals 0. The graph goes through x equals e, y equals e. I draw a secant line through those 2 points and I find its slope. I get this. Now the mean value theorem says if that's the average rate of change, there has to be an x value between 1 and e where the instantaneous rate of change is exactly the same as that average rate of change. And they say find that x value. They want you to call it c. So what you do is you take the derivative, you set it equal to the average rate of change, and you solve for x. So I've got this equals my average rate of change, and I'm just getting x by itself. Since this is a logarithmic equation, I used the log, or the exponential base e, to undo that natural logarithm. And so this was my x value. If you're checking your answers in the back of the book, they'll probably use x equals c rather than x, but c is just a label for a particular x value. And you weren't asked to find this part, but at this x value, y equals this. Now, when you've calculated this c value, you're done. You've answered the question. But I wanted to illustrate this. When x equals this value, y happens to equal this value. And so what we see on the graph is at that x value, x equals e raised to the 1 over e minus 1. The slope of this tangent line there is the same as the slope of the secant line. So the tangent line and the secant line are parallel at that particular x value. Okay, let's do one more. And this one involves a trig function, so we can solve some trigonometric equations. I guess we're not going to solve any trigonometric equations. We're on the interval from 0 to pi. So that means first thing I need to do is check for continuity. And this function is not continuous on the interval from 0 to pi. Darn it, not going to be much work to do here. F of x is equal to this. It's cosine of x plus tangent of x, and tangent is the same as sine of x over cosine of x. So we're going to have problems anytime the cosine of x equals 0. Or alternatively, whenever that tangent function has a vertical asymptote. So this is not cosine plus tangent, this is just tangent. We have the tangent function has vertical asymptotes every time the cosine of x equals 0. And cosine of x equals 0 at all of the odd multiples of pi over 2. So the graph looks like this, and it looks like this, and like this. And we continue. It's not a great graph, but you get the idea. Now the question says, determine whether the mean value theorem applies on the interval from 0 to pi. Well, the interval from 0 to pi is the interval from there to there. This is tangent. See, tangent is undefined at pi over 2. If tangent is undefined at pi over 2, tangent plus cosine of x is undefined at pi over 2. You could also just look at the cosine graph and see when is the cosine 0, and you'll see that cosine is 0 at negative pi over 2, pi over 2, 3 pi over 2, and so on. So we'll say f is not continuous on the interval because tangent of x is undefined at x equals pi over 2. So the mean value theorem does not apply. Okay, so we've seen some examples. If the function fails to be continuous, like that last one, the mean value theorem does not apply. If the function fails to be differentiable, like that absolute value graph we looked at, the mean value theorem does not apply. But if the function's continuous and differentiable, we're guaranteed that there's at least one x value in the interval from a to b, where the slope of the tangent line is equal to the slope of the secant line. Or in terms of applications, the average rate of change of that function on that interval is equal to the instantaneous rate of change at a particular x value. I think the easiest way to remember this and think about this is in terms of this highway speeding example. If you went 60 miles in 2 hours, your average speed was 80 miles per hour. According to the mean value theorem, at some point, and possibly multiple points, in that 2-hour window, I guess we shouldn't say point, let's say some time in that 2-hour window, your instantaneous rate of change, or your instantaneous speed, was the 80 miles per hour. We're not guaranteed that you're going 80 miles per hour the whole time, but the mean value theorem says if you were going an average of 80 miles per hour, at some point you had to be going the average. At some point, there's some instant when your rate of change at that instant is equal to your rate of change on average.